So last week we talked about NFAs, DFAs, various sorts of automata, and the set of languages that they describe. And that set of languages is the set of all regular languages. Now we're going to talk about a set of replacement rules that are more general that can generate a wider class of languages. These replacement rules are called grammars, and we can see by replacing restrictions on them what set of languages we can generate. So first off, what is a grammar? A grammar is a four tuple of four things: VT, VN, S, and P. VT is a set of terminal symbols. These are the things that can't be replaced by something else. They're like the output symbols, if you like. We usually denote them by lowercase letters, A, B, C. There can sometimes be additional symbols or punctuation. It doesn't matter, but usually lowercase letters. V sub n is the set of non-terminals. These are the symbols that can be replaced by something else by a production rule. We usually denote them by uppercase letters, usually S, T, and U. Note that the set of terminals and non-terminals are disjoint sets, so there is never a symbol that lives in both sets. We're going to let V denote the union of these two sets. So V is the set of all symbols, both terminal or not. Capital S, which is an element of V sub n, denotes the starting non-terminal, so the non-terminal from which you start all the production rules from. Almost always the starting non-terminal is denoted either capital S or capital S sub naught. And P, which is a set of production rules, written of the form alpha to beta, where alpha is a string of symbols with at least a single non-terminal, and beta is any string of symbols. That is, they're both elements of V star. So here's an example of a grammar. The set of terminals is lowercase a, lowercase p. The set of non-terminals is capital S, T, and U. The starting symbol is S, and P is the following set of production rules. We usually don't write it in this form. We usually write the grammar in this more compact form. So what does this say? This says S can be replaced with TU, or S can be replaced with epsilon. AS can be replaced with T, or TAU can be replaced with ST. So what do these pipes mean? If I have alpha goes to beta 1, or beta 2, or yada yada yada, or beta n, this is just really shorthand for writing out all the production rules separately. So what is a production rule? So a production rule, alpha points to beta, basically means replace alpha with beta. So given any string that contains alphas inside, you can replace the alphas with betas. So in this string here, we have some string gamma, some string alpha, and some string delta. Because a production rule says I can replace alpha with beta, I can replace this string here with this string here. We denote that with the implication symbol. This is like one production rule applied. If I write alpha an implication with a star and beta, that means from alpha I can get to beta with some sequence of successive production rules applied. Okay, so we'll see that in a moment. And secondly, how do we define the language of a grammar? So the language of a grammar is any possible string of only terminal symbols that can be reached by a sequence of productions. So formally, L of G is a set of all strings W, set of all strings of terminal symbols W, such that from S, some sequence of production rules gets me to W. Okay? So for example, if G is the following grammar, so here I'll just box it in. There we go. So S can be replaced with 1S0, or S can be replaced with epsilon. So here, I can take S, replace with 1S0, and then take this S, and replace it with a 1S0, so we have 1, 1S0, 0. And I can keep doing these replacement rules, replacing S with 1S0 over and over again as many times as I like. And at some point I can take the second transition to replace S with epsilon. So it looks like I can generate any sequence of any number of 1s followed by the same number of 0s. So the language of this grammar is going to be 1 to the n, 0 to the n, where n is greater than or equal to 0. And we know, we've already proven before, that this is not a regular language. If you see video 0814, I go through the proof of that. So already we know that the set of languages that grammars can generate is going to be more general than regular languages, because here I've got a grammar that can generate a language that I know for a fact is not regular. Okay, there are different classes of grammars depending on how many restrictions you apply. In this course, we're only going to be primarily concerned with context-free grammars and regular grammars. So what's context first off? Context is the other terminals and non-terminals that surround the non-terminal and alpha. So for example, here's a grammar here. This production rule here is a context-free production rule because here I can freely replace any S that I see. Here, this production rule has got context. I can only replace S if it's prefixed by an A. So this grammar here is not context-free. So the definition of context-free is that all production rules must be of the form alpha to beta, where alpha is a single non-terminal symbol. So that should be non-terminal. Okay. So all production rules must be of the form alpha is replaced with beta, where alpha is a single non-terminal. So for example, this grammar here is context-free because there's no context on the left-hand side, whereas both of these fail to be context-free grammars because I've got more than one non-terminal or more than one symbol on the left-hand side. Okay, so this one's context-free, these two are not. I will also talk about regular grammars. So a regular grammar is a context-free grammar with extra restrictions on top. So a regular grammar satisfies the context-free property with the additional constraint that all production rules are either right linear or left linear. What's it mean to be a right linear grammar? A right linear grammar satisfies the property that all production rules take a single non-terminal and replace it with a terminal followed by non-terminal, or replace it with a single non-terminal, or replace it with epsilon. So that's what it means to be right linear. To be left linear is the same, but we just swap the order of the first rule. So if you want to be a regular grammar, you have to be right linear or left linear. So here's some examples. This grammar here is a right linear grammar because all the production rules are of this form, so that makes it a regular grammar. Here, this is also a regular grammar because all the production rules are left linear. This grammar here is not regular because I'm mixing up both right and left linear productions. I can't do that. I have to have all of one or all of the other. I can't pick and choose. Because this one here, the non-terminals on the right, and this one here, the non-terminals on the left. I can't mix and match. And the fourth one here is also not regular because I've got a terminal on the left and a terminal on the right sandwiching a non-terminal in the middle. That doesn't match any of these rules here. So this is also forbidden. For a completely arbitrary reason, we usually stick to right linear grammars because it's completely arbitrary which one you pick. So we decided to pick right linear grammars just for the sake of consistency. So those are all the definitions here. That's like a brief outline of what grammars are. And the next videos will go through some proofs we can do and some how to find languages of grammars and all that sort of thing.